Welcome back to the deep dive. Today, we are strapping in for, I think, one of the most intellectually satisfying shifts in organic chemistry.
Oh, absolutely.
We're going to take the familiar stability of the aromatic ring and then force it to completely change its behavior.
Right. It's a complete reversal of what we've come to expect.
So our mission today is to take a stack of sources. We've got detailed mechanistic breakdowns, synthetic schemes, some really critical experimental results, and just extract the exact criteria for making this happen.
It's truly a chapter of transformation. In our previous deep dive, we mastered electrophilic aromatic substitution, or EAS.
Yeah, and that made perfect sense.
It was logical.
Yeah.
The electron-rich pi system of the benzene ring is inherently nucleophilic, so of course it readily attacks electron-poor positive species, the electrophiles.
It's just following its natural inclination.
Exactly.
Benzene acts like an electron donor, but the massive challenge facing chemists, and now facing you, is can we flip that equation? Can we make that highly stable aromatic ring act as an electrophile, an electron-poor target, and successfully welcome a nucleophile, a species carrying excess electrons and, often a negative charge?
And historically, this was considered, well, almost impossible.
Right.
Aromatic stability is built on maintaining that 6-electron pi system.
Mm.
To get a nucleophile to attack means temporarily breaking that stability, which requires overcoming this massive energy barrier.
So there has to be a trick.
There is. The solution, the whole process we're dissecting today, is nucleophilic aromatic substitution, or text SNAr for short. And then there's a surprising alternative, the benzene route.
Okay, so you're going to figure out the chemical cheat codes that drop that energy barrier. We'll explore the 3 highly specific criteria required for the preferred SNAr pathway.
And then we'll break down 2 completely distinct mechanisms that achieve this substitution.
The primary addition-elimination pathway,
And then the more aggressive kind of brute force pathway, the elimination-addition mechanism.
which, I've read, reveals one of the most bizarre and reactive intermediates in all of organic chemistry.
Benzene. It's a fascinating species.
I'm looking forward to that.
By the time we finish this deep dive, you will be equipped to predict not only if a nucleophilic substitution will occur on an aromatic ring, but how it occurs. And you'll understand the deep causal links between substituents, reaction conditions, and the resulting products.
That distinction sounds critical.
It's everything for advanced synthesis.
Okay, let's unpack the setup. So, if we are trying to invite a negative charge, a nucleophile, to attack the ring, we first have to make the ring positive.
You have to make it inviting.
We need to install some kind of chemical drain to suck electron density out. Our sources make it abundantly clear that to favor the standard SNAr mechanism, 3 very specific conditions must be met.
And they are non-negotiable. The first, and really the most foundational condition, is the presence of a powerful electron-withdrawing group, an EWG.
And when we say powerful, the gold standard example that comes up everywhere is the nitro group, text LO20.
That's the one.
It's a group we became familiar with in EAS, but now its function is completely inverted.
Completely. In EAS, we saw the text NO20 group as sort of a chemical adversary, a powerful deactivator.
All right, it slowed everything down.
It withdraws electron density through resonance and induction, and that just crippled the ring's ability to act as a nucleophile.
But now
That exact same withdrawal is the entire foundation of the reaction. It flips the ring from electron-rich to electron-poor.
So the text NO22 group acts like a giant vacuum cleaner,
That's a great way to put it.
and it creates strong, localized, partial positive charges, the little delta pluses, on the ring carbons. Which carbons specifically are most susceptible to this?
Because of the way resonance works, the electron withdrawing effect is strongest and most concentrated at the ortho and pair positions relative to that text NO2 group.
Okay, so it creates specific bullseyes for the incoming nucleophile.
Exactly. This withdrawal is essential for activating the ring toward nucleophilic attack.
But activation is only half the story, right? The sources emphasize that the true mechanistic necessity for the EWG is to stabilize the negative charge buildup that happens during the reaction intermediate.
Yes.
We have to address that energy penalty of temporarily breaking aromaticity.
That's the absolute crux of it. A nucleophile attack introduces a pair of electrons, and those electrons have to be accommodated somewhere.
Right.
If that resulting negative charge, that temporary instability, can't be effectively dissipated or stabilized, the energy barrier is just too high. The nucleophile literally bounces off.
So the EWG has to act as a chemical sink.
A place to safely stash that excess negative charge. This is the difference between activation and stabilization, and you absolutely have to have both.
Got it. Okay, moving to criterion number 2. A good leaving group, an LG.
Hmm.
This substitution is a trade. A nucleophile, Nuc- comes on, and a leaving group, X- must depart. The charges have to balance.
We're just swapping one negative species for another, and this is fundamentally different from EAS, where we kicked off a positive text plus.
Right.
Here, the group has to be able to leave cleanly with its bonding electrons, and the result has to be a stable anion, X-. That's necessary to restore aromaticity.
So we are looking for familiar stable anions as our leaving groups. The halides, chloride, bromide, iodide are excellent.
Perfect examples.
Yeah.
And also highly resonant stabilized groups like sulfonates, things like tosylate, TSO-.
Okay.
And this leads to an absolutely critical prohibition, detailed in the source material. A huge rule.
What's that?
You can never kick off H-.
A hydride ion.
Yes, the hydride ion is the conjugate base of molecular hydrogen. It's an extremely powerful base, which makes it incredibly unstable and therefore a terrible, terrible leaving group.
The energy to make it leave is just insurmountable.
Exactly.
Okay, this helps us analyze some simple scenarios, like the example from the book. I think it was exercise 5.1.
Mm-hmm.
If you have a nitrobenzene ring where the leaving group position is occupied by, say, a methyl group, a text 3,3, the reaction won't proceed via textile, even though you've met criterion 1, you've got the EWG.
That's a perfect test case. If that methyl group were to depart, it would have to leave as a methyl anion, text 3,3-.
A carbanion.
And carbanions are not happy.
Not at all. Like the hydride ion, the carbanion is a very unstable species, a terrible leaving group and a very strong base.
So this confirms the quality of the leaving group is an independent requirement. It doesn't matter how strong your electron-withdrawing group is, the departure has to be feasible.
Correct.
Okay, that brings us to the third, and to me, the most mechanistically puzzling criterion, the positional requirement.
Yeah.
The leaving group must be positioned ortho or para relative to the electron-withdrawing group.
If the leaving group is meta to the EWG, the ring is effectively inert under these conditions.
That's a strict rule.
A very strict rule. But the question is why? Why this restriction? Why does the electron drain need to be specifically ortho or para to the leaving group?
It seems arbitrary until you look at the mechanism. It really suggests that the EWG and the LG have to cooperate structurally.
They do. And that cooperation only works when they are directly across from each other or right next door.
Precisely. This is the ultimate proof that the logic of this reaction isn't just about making the ring a little electron poor. It's about structurally enabling the stabilization of that high-energy intermediate.
And that question is our direct bridge into understanding the mechanism.
It is. So, just to recap before we move on, strong EWG, good LG, and the LG must be positioned for maximum cooperation, ortho or para.
Okay, let's solve this positional mystery by diving right into the accepted SNAr mechanism. It's formally known as the addition-elimination pathway. First, though, we need to clearly establish why the reactions we already know, the ones from alcoholides, Text-NO1 and Text-N2, are complete non-starters here.
This is a crucial distinction. We're dealing with an Text-Stan hybridized carbon atom on the ring, and that immediately just cripples the fundamental geometry required for those mechanisms.
Okay, let's start with Text-N2. We know Text-N2 needs a very specific choreography.
The backside attack.
Right. A nucleophile attacks the electrophilic carbon from the back, pushing the leaving group off the front, and you get an inversion of configuration. But that requires the carbon to be Text-3 hybridized tetrahedral.
And the aromatic carbon is Text-22 hybridized. It's flat. It's locked into the ring structure.
So there's no backside.
There's no backside. That flat geometry combined with the bulk of the ring itself physically blocks any possibility of a backside attack. The transition state geometry simply cannot form.
So Texter is impossible at an aromatic center.
Impossible.
What about Texterine 1? That one avoids the geometry issue because it happens in 2 steps.
Right. Leaving group leaves first, you get a carbocation.
And then the nucleophile attacks.
The problem with Texas-N1 is the intermediate. If the leaving group departs first from the aromatic ring, it forms what's called a phenylcation.
And that sounds unstable.
Oh, it's highly unstable, for 2 big reasons. First, the positive charge is locked into a Text-22 orbital that sits 90 degrees outside the plane of the ring.
So it can't be stabilized by resonance?
It gets no help from the pi system at all. And second, the Text-2 orbital is fundamentally more electronegative than an Text-A3 orbital, so forming a positive charge there is just energetically catastrophic.
So because the intermediates for both of our standard substitution mechanisms are either geometrically impossible for the Text-NSN station state, or energetically prohibitive for the text and after rephenocation, we absolutely require this new bespoke addition-elimination mechanism.
We do. So let's walk through it. Let's use the example of chloronitrobenzene reacting with hydroxide, OH-.
Okay, step one, nucleophilic addition and the Meisenheimer complex. So the nucleophile attacks the carbon atom that's holding the leaving group.
Right.
I have to ask, isn't breaking aromaticity still an immense energy hurdle here, even with the EWG? How fast is this first step compared to, say, nitration in EAS?
It is still the rate-determining step, absolutely. And yes, it costs significant energy to break that pi system. But the EWG immediately pays back a portion of that energy cost through stabilization. When the nucleophile attacks, the pi electrons shift, breaking aromaticity and generating the key intermediate, the Meisenheimer complex.
This complex is the defining feature of the texture reaction, and unlike the positively charged sigma complex in EAS, this is a negatively charged intermediate.
It's a cyclohexadianyl anion.
Precisely.
The whole goal now is maximizing the stability of this temporary negative charge.
Okay.
The charge is delocalized via resonance over 3 carbon atoms in the ring, the ortho and para positions relative to where the attack happened.
But here's the critical point, right? The one that explains criterion 3.
This is it. That stabilization is insufficient unless one of those resonance structures can place the negative charge directly onto the electron-withdrawing group itself.
So if the Texanoda-2 group is ortho or para to the attack site,
Yes.
we can draw a resonance structure that puts the negative charge directly onto one of the highly electronegative oxygen atoms of the nitro group.
And that is the moment of chemical salvation.
Huh, I like that.
Oxygen is perfectly suited to stabilize that excess electron density. You can think of it as opening a highly specialized, stable vault where this explosive negative charge can temporarily reside.
The reservoir.
It's the reservoir we keep referencing. This makes the Meisenheimer complex significantly lower in energy than it would be without the EWG, and that allows the reaction to proceed under relatively mild conditions.
Okay, that immediately clarifies the positional requirement. So why does the meta position fail?
Because if the leaving group and the EWG are meta to each other, when the nucleophile attacks, the resulting negative charge, even as it delocalizes across the 3 ring carbons,
It can never land next to the nitro group.
it can never be positioned next to the Texano-2 group in a way that allows a resonance structure to place the charge onto the oxygen atom.
So if the nucleophile attacks a meta-substituted ring, the negative charge is still delocalized, but it's just stuck on carbon atoms.
Only on carbon. And without opening that oxygen reservoir, the intermediate is just too high in energy. The energy barrier for the meta attack remains prohibitively high.
So the positional requirement isn't arbitrary at all. It's a strict mechanistic mandate.
It's all about maximizing resonance stabilization.
Okay, so once that stabilized, negatively charged Meisenheimer complex is formed, we move to step 2, elimination and restoration of aromaticity.
Now, the system just wants to shed that excess energy. The negative charge that was stored in the reservoir flows back into the ring,
Which instantaneously causes the expulsion of the leaving group, the chloride.
and the aromatic ring reforms. Substitution is complete. It's a perfect, rapid, 2-step cycle. Addition, followed by elimination.
However, the sources guide us to a subtle but necessary point here about the practical application of this chemistry. Post-reaction proton transfers. This is where we have to account for the strong basic conditions of the reaction itself.
Precisely. If we use sodium hydroxide, text NaOH2, as our nucleophile, the resulting product is a nitrophenol, a substituted benzene with an OH group.
But phenols are mildly acidic.
Right. And the reaction mixture is highly basic. It's full of text NaOH.
Meaning that the instant the substitution product forms, the hydroxide that's still in the flask will immediately strip the mildly acidic phenolic proton.
And you get a negatively charged phenoxide anion.
You've got it. So if you stop the reaction right after the substitution step, you don't actually have your neutral nitrophenol product.
Nope, you have the stable phenoxide salt. And this is why the typical reaction scheme always includes a second mandatory step.
The workup.
The workup, which involves adding a strong acid like Tex3-Tex plus lol after the substitution is complete.
And that acidic workup is what pertonates the stable phenoxide anion back to the desired neutral OH product, the nitrophenol.
Exactly. Recognizing and including those 2 final steps, the immediate deprotonation under basic conditions, followed by the protonation during the acid workup, that is the hallmark of a deep, practical understanding of detorquination.
We've established the strict 3-part criteria for the addition-elimination, the text SNAr mechanism. But what happens when we intentionally break those rules?
Mm.
What if the starting material lacks that necessary EWG reservoir?
Well, if you take simple chlorobenzene, which has no EWG, and you treat it with hydroxide under standard SNAr conditions,
And nothing happens.
you observe no reaction. The Meisenheimer intermediate is just simply too high in energy to form.
And yet history shows that substitution can be forced.
It can.
If we use brute force, either extreme temperature or extremely strong bases, and this necessity for extreme measures, that hints that a totally different pathway must be operating.
A totally different one. And that pathway is the elimination addition mechanism. Let's look at two classical examples of this forced substitution. One is the historic Dow process, which synthesizes phenol by treating chlorobenzene with TeX-NaOH at incredibly high temperatures,
Light. How high?
typically around TeX-TeX.
Wow, that's a serious industrial process. You're not doing that in a lab hood.
Absolutely not. Another common laboratory method, which is often used to install an alamine group and a TeX-10H22 group, uses an exceptionally strong base sodium amide, TeX-1082N, in liquid ammonia,
Okay, so a super base.
a superbase. And this allows the reaction to occur without the extreme TeX-10 heat, and it yields aniline.
So if TeX-tank fails, what is the definitive proof that a new mechanism is at play? How do we know it's not just some weird version of TeX-aniline?
The proof came from a brilliant piece of chemical detective work involving isotopic labeling.
Okay.
This is a perfect example of how chemists track invisible processes.
So walk us through that experiment.
Researchers synthesized chlorobenzene, where they specifically labeled the carbon atom bearing the chlorine with the heavy, non-radioactive isotope carbon-13.
So they put a little tag on that one carbon.
A chemical tag, exactly. This labeled carbon is the starting point. They then reacted this specific compound with sodium amide to produce aniline.
Okay, so if the substitution had proceeded via a simple direct mechanism, the TeX and H2 group should only attach to that original labeled TeX-2 carbon.
That was the expectation. But the analysis of the final aniline product revealed this fascinating and confounding result.
What was it?
The product was a perfect 50-50 mixture.
50-50 how?
Half of the product had the TeX-NH22 attached to the original TeX-42 labeled carbon, just as expected.
And the other half?
The other half had the TeX-NH22 group attached to the carbon adjacent to the labeled site.
The substitution group moved.
It moved. This displacement proves that the reaction is not a simple direct attack. It requires an intermediate that somehow erases the chemical memory of where the chlorine atom originally sat.
And that intermediate is benzene.
That is benzene. The mechanism, elimination addition, describes the reverse sequence of events from TeX-TAN.
Okay, let's break that down. Step 1, elimination and the benzyne intermediate. This is where the incredibly strong base shows its true colors.
Yes, TeX-NaNH22 is a terrible nucleophile, but an outstanding base. So it acts as a base first.
It's not attacking the carbon with the chlorine.
No. It removes a proton, an H, from a carbon adjacent to the carbon bearing the leaving group.
Okay.
This deprotonation is immediately followed by, or even synchronized with, the departure of the leaving group, the chloride.
And the result is benzene. The source describes it as a benzene ring containing a triple bond forced within the ring structure.
Yes.
We need to understand the molecular strain here. How is this triple bond formed, and why is it so incredibly reactive?
Okay, so a standard triple bond, like in acetylene, is formed by the linear overlap of CPO orbitals.
Right, 180-degree bond angle.
Exactly. The carbons in benzene are CP22 hybridized, demanding a 120-degree bond angle.
So there's a problem.
A big problem. When you form benzene, you are forcing the two CsP22 orbitals, which normally participate in the ring's sigma framework, to overlap sideways to form that additional pi bond inside the ring.
So you're forcing CsP22 orbitals to act like CsP orbitals in a system that demands a 120-degree angle. This must introduce phenomenal angular strain.
It creates immense strain. The CP22 orbitals simply cannot achieve the necessary linear overlap. The resulting triple bond is incredibly weak, highly reactive, and just desperate to break.
So benzene is a fleeting intermediate.
Oh, it's the chemical equivalent of an energetic teenager locked in a closet. It is desperate to react and open itself up.
Okay, so the benzyne intermediate is unstable, but it successfully completes the elimination step without relying on an EWG reservoir.
That's the key.
Now we move to step 2, nucleophilic addition to benzyme.
Right, so because the triple bond bridges two adjacent carbon atoms, and in the case of simple chlorobenzene, those two carbons are chemically equivalent, the incoming nucleophile attacks the triple bond.
And critically.
Critically, It can attack either carbon with equal probability.
Ah, okay. So if the nucleophile attacks one carbon, the negative charge is placed on the adjacent carbon, which gets protonated later.
Hmm.
And if the nucleophile attacks the other carbon, the charge is placed on the first carbon.
And that inherent ambiguity of addition is the elegant explanation for the 50-50 mixture that they observed in the labeling experiment.
Because the original chlorine site and the adjacent site become interchangeable points of attack after the benzyne intermediate forms.
The two pathways are perfectly symmetrical in terms of energy.
This confirms that the benzyne intermediate is responsible for the apparent movement of the incoming substituent.
Absolutely.
And the whole process is named elimination addition, reflecting that reverse sequence of steps compared to the text SNAr pathway.
The choice of mechanism is entirely a function of the starting material's stability and the harshness of the conditions.
So we now have three primary tools for manipulating aromatic rings. EAS, the addition-elimination path, and now the elimination addition path, the benzyne one.
Right.
The expert skill, then, is instantaneously looking at a reaction and determining which road you need to take.
And we can streamline this. We can create a strategic decision tree that minimizes any guesswork.
Okay.
You always begin by assessing the reagent's core chemical identity.
Question 1. Are the reagents nucleophilic or electrophilic?
Exactly. If you see positive or electron-poor species like textenone-2 with acid, text-2 with a Lewis acid, or an acylium ion,
You're dealing with an electrophile.
you are. And the mechanism is almost certainly going to be electrophilic aromatic substitution, EAS.
Okay, but if you see strong negative or electron-rich species like hydroxide or alumide or alkoxides,
Then you have nucleophilic reagents,
Yeah.
and that means you have to proceed to the next critical check.
which is question 2. Does the aromatic ring satisfy all three criteria for texting?
And if the answer is yes, you have a strong EWG like a nitro group. You have a good LG like a halide, and that LG is positioned ortho or para to the EWG.
Then the path of least resistance is available.
It is. You expect text to SNAr additional elimination. These reactions, while they might require some heat, they proceed under relatively mild conditions because of the stabilization you get from the Meisenheimer complex.
But if the answer is no,
Yes.
you're missing the EWG, or crucially, the EWG and LG are positioned meta to each other, so you fail criterion 3.
Then the path of high energy must be taken. You have to expect the forceful elimination addition pathway.
The benzyne route.
That's the benzyne route. And that mechanism requires the harsh conditions, extreme heat, like Tech 6, or those exceptionally strong bases like sodium amide, to force that initial elimination step.
Let's dedicate some serious time to the most critical exception that really tests this logic.
The meta case.
The meta exception, as explored in exercise 5.19, we have metachloronitrobenzene reacting with text NaOH under heat.
This scenario is fascinating because on the surface, it seems like SNAr should work.
Right. You've got a powerful nucleophile, the hydroxide. You've got a great leaving group, the chloride.
And you have the most powerful EWG, the nitro group.
But the positional requirement fails. They're meta.
And because the textone-2 cannot stabilize the Meisenheimer complex, if the nucleophile attacks at the position bearing the chlorine, SNAr is completely ruled out.
Even with the nitro group present.
Even with it there. Therefore, the reaction must proceed via the benzene intermediate.
And this is where the predictive power of understanding benzyne comes into play, because the product distribution gets complicated.
It gets very complex.
Since the mechanism is elimination addition, the strong base will remove a proton adjacent to the chlorine.
Right.
But now the two adjacent carbons are not equivalent.
They're not, because of the presence of that textone-2 group 3 carbons away. So the base can remove the proton on the carbon closest to the nitro group, leading to one specific benzyne intermediate. Or it can remove the proton on the carbon furthest from the nitro group, leading to a different benzyne intermediate.
And those two pathways don't happen 50-50.
No, the base will favor removing the proton that leads to the most stable carbanion intermediate, although both are generally accessible.
So you get a mix of benzyne intermediates, and then the incoming nucleophile attacks the triple bond.
Right. But now the triple bond sites are often not equivalent either. In the benzyne formed from eliminating away from the nitro group, the nucleophile can attack either carbon, leading to two distinct products.
And for the other one?
In the benzyne formed closer to the nitro group, the nucleophile will generally favor the carbon that places the negative charge on the adjacent carbon closest to the EWG, because the nitro group can inductively help stabilize that adjacent carbanion.
Wow. Okay, so the key takeaway is that the benzyne pathway, once it's forced, is highly promiscuous.
That's a good word for it.
Instead of a single clean product, like in SNAr, you can end up with a mixture of potentially 3 different positional isomers.
Yes, the original substituted product and 2 versions of the moved substituted product.
And predicting all of those possible products based on the non-equivalent elimination directions and the subsequent addition ambiguity, that's the ultimate confirmation that you've correctly identified the Benzyme mechanism.
It really is.
Okay, finally, let's bring this all back to practical synthesis goals. Why are we dedicating an entire deep dive to reactions that are so difficult or require such extreme conditions?
Because the substitution of hydrogen via EAS is easy, but until this chapter, we had no clear, general way to directly install a hydroxyl group, an OH group, or an amine group, and a text NH2 group onto an aromatic ring. These nucleophilic methods provide that crucial missing link.
So EAS can install a nitro group, a halogen, an alkyl group, but not the OH or text NH2 directly. These new mechanisms complete our synthetic toolbox.
They do. And the standard synthetic strategy, starting from basic benzene, is a reliable 2-step sequence using the elimination-addition pathway.
Okay, so step 1 is always setting up the leaving group, chlorination. Start with benzene and perform EAS using textphils 2,2 and textalis 3 to install the chlorine atom. This is our placeholder.
And step 2 is the forced substitution via elimination addition.
If your synthetic goal is to yield phenol, the OH group, you have to use the historic Dow process conditions.
This is textsil-AT, followed by the acidic workup. It really demonstrates the chemical necessity of extreme temperature to force the reaction without an EWG present.
And if your goal is to synthesize aniline, the text NHUD2 group.
Then you utilize the immense specificity of sodiamide, text NHRT, in liquid ammonia, again followed by the acidic workup.
And the choice of sodium amide over sodium hydroxide
Is often strategic in a lab setting because it facilitates that initial elimination step more efficiently. Sometimes it lets you avoid the brutal heat of the Dow process.
So these methods provide the only viable route to these key functional groups in early aromatic synthesis.
That's right.
We began this deep dive by challenging the very nature of aromatic stability, a system that really resists attack. And we found that nucleophilic substitution is possible, provided we meet the energy demands through some very careful design.
And we identified 2 fundamentally different ways the substitution occurs. Path 1 is the standard, preferred, and relatively mild text-NOVA pathway.
The addition-elimination.
Right. It's fast, but it demands all 3 criteria, the EWG, the LG, and that positional cooperation, ortho or para, that's required to stabilize the negative Meisenheimer complex.
And path 2 is the forceful elimination-addition mechanism.
The brute force method.
Reserved for when textar fails. It requires extreme conditions and proceeds through the highly strange, short-lived benzyne intermediate.
And the penalty for this forced route is the loss of control. You often end up with a mix of positional products because of the ambiguous attack across the triple bond.
So the key takeaway for anyone trying to predict aromatic reactions is that the details are paramount.
They're everything. You have to first classify the reagent. Is it a nucleophile or an electrophile?
And if it's a nucleophile?
You must meticulously check the positions of the substituents and the reaction temperature. These microscopic details dictate the entire macroscopic outcome, from mechanism choice to product distribution.
And the journey to understanding this required some brilliant experimental work. The sources highlight the ingenuity of that isotopic labeling test, tracking the text atom, which offered the definitive proof of the seemingly impossible benzyne intermediate.
And that raises a final provocative thought for you to carry forward, whether you are tackling organic chemistry problems or investigating a complex system in any field.
Okay.
When studying any transformation, how often is the most significant discovery not the final product that you can isolate and weigh, but the detection and characterization of a highly unstable, fleeting intermediate?
A transition state that must exist for the process to occur at all.
Yes. Exactly. Chemistry often finds its greatest insights in moments of extreme instability.
Food for thought indeed. Thank you for joining us on this deep dive into nucleophilic aromatic substitution.
Until next time, keep following those electrons.